Okay, so we've looked at a way to evaluate a process layout, but is there some way we can come up with a good process layout just with initial data? Again, in the previous example, I probably could have eyeballed that, but if the problem was a little bigger, what would I do? Well, we're still going to work with a small example here in this procedure, but again, this is an approach that works well for larger problems, and it relies a lot on the human ability to spot patterns graphically and then quickly make adjustments um, to consolidate certain relationships at the expense of others. This approach is called systematic layout planning, or SLP, and the way it works, well, first, all work centers are termed activities. Okay, so instead of placing work centers, we talk about trying to place activities. Each activity is represented by a node in a graph. So here I've got 4 activities, and in this example, a little different than the last, I'm representing the activities or work centers as letters rather than numbers. And what I do is I draw a line or multiple lines between each pair of activities to indicate the nature of the relationship between those two activities or work centers. So, for example, 3 lines between work center A and work center B, or activity A and activity B, generally means that there's a pretty strong relationship between those two activities, and I want to put them fairly close together. On the other hand, a jagged line like I have here between activity C and activity D means I really don't want to have those together. Maybe C is painting and D is grinding, and I don't want the dust from grinding getting into the paint booths. So I can represent not just the importance of having two activities close together because of, say, the importance of minimizing movement costs, and they've got a lot of movement between them, but I can also represent the importance of not having a pair of activities together. So this is a fairly flexible approach in trying to come up with an initial layout. It has a little bit of a broader coverage than just transportation costs and trying to minimize transportation costs. So the first thing that systematic layout planning does is assign each pair of activities a relationship code. And there's a limited range of codes, cleverly called A, E, I, O, U, and X. Basically, A represents the relationship between a pair of activities that is absolutely necessary. E is one that's extremely important. I is very important. O of ordinary importance. U is unimportant. And then an X relationship is an undesirable relationship. This is the relationship that's represented with a jagged line in the graphical representation. Again, these aren't particularly clever. I didn't make them up. This is the actual terminology used. So let's take a look at our earlier example where I had the 3 work centers, and hence now called 3 activities. And with 3 activities, there's 3 possible pairs, 1 and 2, 1 and 3, and 2 and 3. And if you recall, looking back at the previous slide, there was no volume of flow, no loads per day flowing between 1 and 2, but there was 300 loads per day moving between 1 and 3, and 200 loads per day moving between 2 and 3. So if I was going to use volume as a basis for assigning these relationship codes, I would give a U for unimportant to this activity pair. I would give an A for absolutely necessary to this activity pair, and an I for, well, of ordinary importance to this activity pair. Again, obviously there's a bit of a judgment call on saying, well, is this an I or an E relationship? That's a decision that the planner has to make. So if I made those assignments of relationship codes, then what do I do next? Well, I want to get this information in graphical format because I want to make use of the planner's visual pattern recognition abilities. So I'm going to represent each A relationship with 4 lines between those activities in the diagram. The I relationship is going to get 2 lines. U relationship gets no lines. Okay, and these are the number of lines or type of line that are given to the other relationships. But again, our simple example, we've only got 3 relationships. So I end up with an activity relationship diagram that looks like this, where I've got 4 lines connecting 1 and 3, because that's where most of the volume of flow was. I got 2 lines connecting 2 and 3. It had some volume of flow, but not as much, and then no lines connecting 1 and 2. And the way you think of this now is these lines are like rubber bands. So the more rubber bands, the closer those activities need to be, and the fewer the rubber bands, they don't need to be nearly as close. So if we're trying to lay this activity out, or these activities out, in a long building like this with 3 rooms, it becomes pretty clear that what we need to do is put 3 and 1 close together. 2 and 3 need to be reasonably close as well, not as close as 3 and 1, and then there's no need to have 2 and 1 close together. So I end up with a relationship, with a assignment of activities or work centers to rooms that looks like this. 2 goes in A, work center 3 goes in room B, and work center 1 goes in room C. Again, here's my total cost equation from before. The volume of flow between 1 and 3 and 2 and 3, that hasn't changed from the previous equation, but the distances between the 2 pairs of work centers has. Now 1 and 3 are only 20 feet apart, and 2 and 3 are 40 feet apart. Right? So when I do the math here, I get a total cost in terms of footloads per day of 14,000, which, if we go back and take a look at the previous example, is much lower than 22,000. So I've improved upon this initial layout in this very simple example. Now this may seem like overkill for such a simple example, but I've seen this procedure used when there's been close to 50 activities, and the diagram is much more of a mess, but you'd be surprised how in even such a large diagram as that with 50 nodes, that some of the activities really stand out, and it becomes pretty easy to cluster groups of tightly interrelated activities and place them in the facility.